Hello there. This is the first of the live lessons. Just to go through what I'm going to do tonight, I'll have a series of questions which I've written myself, so they're not past paper questions. Might be an idea if you want to, for some of them, the first few questions you'll not need to write anything down, but for the questions after that you might want a pen, a ruler, piece of paper, a calculator and so on. Up to yourself. And of course, once the session's finished, this will be available on YouTube. You can go through this again and pause at any time so you can see the questions, maybe try them out and then see the answer. Right, let's get started with the first question, or at least the first picture, which is this one. Oh, I realise I've made a mistake. What I was supposed to be showing you. 2 seconds. Unfortunately, I've given you the answers there. There we are. That's where I should have started. I should have been showing you this one, and of course you've seen the words before. What I'm actually going to do, I'm going to show you 20 circuit symbols. Just make sure, now obviously you've seen the names up, but do you actually know the names of these? If you were asked to draw a circuit diagram, would you be able to draw these symbols if you were to see it in a circuit diagram? Would you be able to identify them? So what I'm actually going to do, I'll let you see them for a second. I'll go back to the screen that you saw before with the names. There will be another 10, and fingers crossed we'll pick the right screen next time. Names will be hidden. So if I then pick this slide here, there we go, those are the names. Now I guess the one that I really want to pick out, hopefully most of these should be fine. The ones I'm going to pick out are obviously these two, which can be confused. I guess what you would normally call a battery, you go to a shop, you buy a battery. In physics, that's what would normally be called a cell. This is the symbol for a cell. If you're placing more than one cell in series, that makes a battery of cells. So that's something that actually came up in the 2015 paper, that you were asked to draw a circuit with a battery. If you'd drawn this, if you'd drawn the cell, not really what we were looking for. We're looking for this symbol here. So it looks like two cells together with at least it's got a dotted line with at least 3, or dashed line you could say, with at least 3 dashes, and there is a difference between these two. So make sure that you know that difference. Everything else, I would imagine everything else should be instantly recognizable. Fingers crossed. You just take a look at it and make sure you know all of these. As I said, you can look at these later. Now this one, that's a little bit more difficult if I go to the next screen. So there we go. We've gotten it right this time. We've got the slide with the names obscured. I'm going to give you a second just to look at that. What I will say is that one of these, I'm going to point at that in a second. This one here, this has normally got a dotted line around it. Just to save space, I've actually not drawn that. So this is a component which actually consists of 2 parts. If I can maybe tell you that this part on the left is the coil, acts as an electromagnet. This part on the right, that's the switch. Okay, so take a good look at those, and I'm going to show you these answers. And here they go. Again, most of these hopefully should be fairly straightforward. We'll be looking at this one if there's time later, and remember I'm going on till roughly 7 o'clock. Depends. If I run out of time, then obviously I'll just continue. I hope to go over the circuit basics, I guess, the circuit symbols, a few questions about electrical circuits, talk about potential dividers, resistors in parallel, and transistor switching. So obviously if I run out of time, I'll just continue from that point, transistor switching circuits, next time. Right, so as I said, this is consisting of 2 parts. So this is a relay. The relay coil is the part on the left hand side, acts as an electromagnet. When you have a current in this relay coil, that then usually would then close this switch, and the left hand side would be connected to one circuit and the right hand side to a second circuit. Now as I said, you'll hopefully see a circuit with a relay in it later. It's not just enough to know the symbols, you need to know what, say, or how they operate. So LDR, that's obviously a light dependent resistor. Anything with arrows pointing in the way shows that in this case actually the resistance is going to change when you shine light on it. So the arrows obviously signify the light, and when you shine light on that, its resistance decreases. This one also has arrows pointing towards it. This is something, I guess it's better known as a solar cell. So remember, in the last slide what we saw before was the actual symbol for the cell, and we've got arrows pointing towards it. So obviously this is something to do with light. When you shine light on the solar cell, which is I guess also known as a photovoltaic cell, shine light on that, it creates a voltage. The brighter the light, the higher the voltage. Okay, as we said, this one, when you shine light on it, its resistance decreases. We've spoken about the switching action, and we'll talk a little bit later about the relay. The thermistor, you heat that up and its resistance then decreases. Right, so there we go. Now, as I said, for some of these questions you'll need a piece of paper. You might want a piece of paper. So this would be the first of them. So I'm going to find another question, which is this one. And it says that a group of pupils are given the following equipment and asked to calculate the power output and resistance of a lamp. You wouldn't normally be asked to calculate both. I've just put this in the question, I guess, to cover all options. So the pupils group given an ammeter, a voltmeter. I'm not going to follow that with the hand all the way along. An ammeter, a voltmeter, 12 volt battery, not a cell, 12 volt battery, a lamp, and connecting leads. Question then asks, part A, draw a circuit diagram to show how the pupils should set up the equipment. Now, I'm not going to sit here and draw the whole diagram. What I will say is, don't just draw it by hand, like so. Now, I've already started. I guess, is that a mistake? It doesn't need to be a mistake. If I was to do this, and remember those dotted lines, like so, and let's see along here, what am I going for? A lamp, and I'm working out the power and the resistance of the lamp. Now this is already a bad start, because as I said before, you should be starting with a ruler, or you should be using a ruler. Move the paper up a little bit, and let's see, I'll go all the way along. Of course I want to, if I'm working out the resistance and the power, I really want a voltmeter in parallel. Remember, voltmeters in parallel and ammeters in series. So there you go, you want the voltmeter in parallel with the lamp. And yes, it is a deliberate mistake. I've left no space here for the ammeter, and that doesn't look good. Okay, so it does say now, this is, as I said, this is done on purpose. It says at the front of your test that you should be using a black or a blue pen. Okay, it also says in the specimen paper, don't use gel pens, but use a black or a blue pen. What I should have done really here is that I should have thought a little bit more before I drew the circuit. So just, as I said, plan exactly where you're going to place the components. What you could do, I mean, it does say to use a black or a blue pen. Often in class you're asked to draw diagrams in pencil, so that's not recommended, but possibly just for the circuit diagrams you could use one of these pens that actually allows you to rub out this line. Just for the circuit diagrams. Other questions, just use a normal pen, I guess. So yeah, that would have allowed you to score this out and then draw in the ammeter. Looks an awful lot neater. Possibly could have lost marks for this as well. It's not very clear, this symbol for the ammeter. Now if I show you as well, I should have the answer for this, and this is it here. There we go, and a few pointers as well. So as I said, think of the position of the ammeter and voltmeter before you draw it. A voltmeter, only one place it can actually go. So if we want the power of the lamp and the resistance, as I said, the question maybe only would ask you for one thing. You need to have that voltmeter in parallel with the component. So it needs to be across the lamp. This ammeter, as long as that's in series, not a problem. Okay, so and what I mean by that, they're not just one position. So the ammeter could go here, could go here, anywhere in series with this lamp. If it's a parallel circuit and you want the resistance or power of this lamp, as long as this ammeter's in the same branch as the lamp. Okay? But what you don't want to do is this. Okay, don't make that mistake. As I said before, don't confuse the battery with the cell. And last but not least, I've not done it here, so I've made two mistakes. I've not used a ruler. I've not planned where that component's going to be. Alright, there you go. So that's part A, just to get it started. If I can find the next question, it looks a little bit like this. So remember, we saw this circuit and we've been asked to work at the power, asked to work at the resistance. So here's some typical data. What does it say? The group's results are shown in the table below. Use these results to calculate the power output of the lamp and its resistance. Now, what I've said several times before is that sometimes pupils will make mistakes in writing down equations or manipulating an equation. What I would always do, even though you think you know the equation, I would always just write down the equation and checking it in the relationship sheet. Doesn't take an awful lot of time to check. So the first thing we would do is look at the relationship sheet. We need the power, so let's see, this is part B, and the power output P is equal to, so we're told the current and we're told the voltage I times V. I'm not going to go to the calculator view. So 3.0, so 3 for the current, voltage is 12, is equal to 36 watts. Now, it's not applicable in this question, but obviously I've written this answer as two significant figures. It's as well, I guess, to mention it now as any other time. The data itself that I've used to work out that power, P is equal to I times V. Current is given as two significant figures. Voltage is given as three significant figures. And the general rule is that you should give your final answer with the same number of figures, significant figures, as the data in the question which has the least number. So current is only written to two significant figures, so technically we should be writing our answer as power to two significant figures. Now, what else were we asked to work at? We were also asked to work at the resistance, so we're going to go up, and as I said, I've only really written this question to work at the power and the resistance. But normally you would normally just be asked to work at one, I guess, or it certainly wouldn't be asked to work at both in the same part of the question. Now, what I've done here as well, I've gone straight to that R is equal to V over I from Ohm's law. Now I've written it right. Of course, I've manipulated that equation right, but I would always say, just in case there's any mistakes, to actually start with the equation, which is in the relationship sheet, which is obviously V equals IR, and then rearrange it. You will not get any additional marks for rearranging, but if I was to make a mistake and say R is I over V, I get nothing. If I write the equation as it's shown in the the relationship sheet, then at least I'll get 1 mark. Okay, so R is V over I is equal to 12 over 3 is equal to 4 ohms. There we go. Now that was the first circuit and the first question. A next one looks a bit like this. If I can again find it. There we go. Now this shouldn't be too tricky, I would hope. Obviously it's resistors in parallel. It doesn't catch out everyone, but there are some common mistakes that we see. Again, look at the relationship sheet. Sometimes you'll see people work this out perfectly and write down that RT is 1 over R1 plus 1 over R2 plus 1 over R3. Everything else after this would be perfect. But of course, if you're writing the equation wrongly, you get nothing at all. Doesn't matter what you're doing after this. If you've written down the equation wrongly, no marks. So again, I know I'm saying the same thing, but check that relationship sheet. It's there for a reason, so it'd be as well use it. So 1 mark for that. 1 mark, of course, for the substitution. 1 over 12 plus 1 over 12 plus 1 over 6. Now, obviously, I want to change this 1 over 6 to 12ths. So we've got 1/12 plus 1/12 plus 2/12 is equal to 4/12. What some people would then do at this point, I mean, I have seen it, that they would then work out 4 over 12 and that would be their answer as the resistance. That's not what you want to do. Sometimes you'll also see that they're writing 4 over 12 equals 12 over 4. That's bad form. What you really want to do in a separate line, now remember what we've got so far is 1 over t is 4 over 12. So if 1 over RT is 4 over 12 on a separate line, the total resistance, we're flipping this upside down to give us RT over 1, which is RT, the effective resistance. So RT, it would be, as I said, we're flipping this side upside down, so we're flipping this upside down. 12 over 4 is equal to 3 ohms. There we go. A question like that would normally just come up in the multiple choice question. Let's see now. There is a lesson that's going to go online at some point, talk about parallel circuits, series circuits, and mixed parallel and series circuits. And it's going to mention the position of ammeters, voltmeters, and so on and so forth. There's a second part to this question, and it is here. There we go. This one obviously just goes over the fact, I guess, the order, if you do have a circuit like this which has a parallel component and a series component, we've just worked out the effective resistance of these 3 resistors would be 4 ohms. So if you're given a circuit like this, then you would always work at the resistors, or the effective resistance of these resistors on the right hand side. We've worked out that that's 4 ohms, and then obviously would add the 4 ohms in the left. So in this, sorry, we worked out that this was 3 ohms, didn't we? Yes, we did. Yeah, so sorry, that was 3 ohms. So as I said, this would be the 3 ohms plus the 4, sorry, would be 7 ohms. So in total this would be 7 ohms. There you are. Now I think we're going to change the subject slightly at this point. And this question here, which is getting on a little bit for an introduction to potential dividers. So let's see, what does the question say? The question says calculate the current in the 15 ohms resistor. Now we've said about the position of ammeters. So an ammeter could go here, it could go here. If we just want the current in the 15 ohm resistor, some people think that that would mean the ammeter has to go in before the 15 ohm resistor. But of course, in a series circuit, the current's the same all the way around that circuit. So the current, it doesn't matter that it's saying in the 15 ohm resistor, the current in the 5 ohm resistor would be exactly the same. Okay, so basically all we're actually doing is using, remember again, as I said before, write the equation as you see it in the relationship sheet, just in case that you're going to manipulate it wrongly, unless you're feeling brave. So V is equal to I times R, therefore I is equal to V over R. In this series circuit, the current would depend on the total resistance in the circuit, and the total resistance in the circuit would be 5 plus 15 would be 20 ohms. So I is equal to V over R is equal to supply voltage is 12, total resistance is 20, and if I'm dividing 12 by 20, again, I'm not going to go to calculator view, I'm not doing anything fancy in the calculator, 0.6 amps. Now again, just to say that the final answer would have the same number of significant figures as, so I've got 2 significant figures here. The data Well, obviously this has 3 significant figures, 2 and 2. So the least number of figures in the data is 2. I should be writing my answer as 2 figures. I would say 99.9% of the questions I've seen in exams, if you write 3 significant figures, you are actually allowed, you'll get away if you have anything up to 2 too many or 1 too few. It tends to be if you write 3 significant figures in your answer, then you'll not lose marks. But it's good to know the actual rule. Now, what's the next thing we have to do? We worked out the current. As I said, this is like a potential or voltage divider. So part A, we worked out the current, and if we want the voltage across the 15 ohm resistor, we're just going to use this same equation. But let's say I was going to call the resistor on the left, the 5 ohm resistor, if I was going to call that R1, and I was to call this resistor R2, then the voltage across R2, V2, is equal to the current I times the resistance of that second resistor. I don't need to write these numbers here, that can just be written as V equals IR. So as we said, the current was 0.6 and the second resistance was 15, and that should give us 0.6 times 15 gives us 9 volts. Just check your answer obviously isn't larger than the supply voltage. It's impossible. Okay, now you will sometimes see that when you're marking tests that despite the fact the supply voltage is 12, we've got an answer of 300 volts. Not possible. So this, you should know that what's going to happen in this circuit is that, of course, the supply voltage is split between these 2 resistors. This is the largest resistance, and the largest resistance will end up with the largest voltage across it. In fact, this is 3 times larger than this resistance. So the voltage across this resistor, 9, would be 3 times larger than the voltage across this resistance. Now, I could use this equation again to work out if I wanted the voltage across the 5 ohm resistor, but I wouldn't need to. I would just take the 12 volts and subtract the 9 volts across the 15 ohm resistor. Of course, that would give me 3 volts across this one. There we go. Now, let's see. I'm going on to another circuit. So that, as I said, this is a quick introduction to potential dividers. Oh, sorry, I think I've gone on to the wrong one there. So I think the one I actually want. There we are. We'll look at that other one in a minute. Talk about potential dividers. This question says a pupil sets up an electric circuit that's shown in the diagram. Calculate the voltage across the 15 ohm resistor. Now I guess I've shown how you could do that, and it's good to know this method. There are actually, well, there's more than one method anyway to work out the voltage across the 15 ohm resistor. We could use exactly the same method here. So we would use I is equal to V over R. We divide the supply voltage, which in this case would be 5, by the total resistance, which would be 15 and 7 is 22. That would give us the current. And if we want the voltage across the 15 ohm resistor, we'd use Ohm's law again, multiply that current we've just calculated times 15, and that would give us the voltage across it. But what you could do, so remember there are 2 methods at least that I'm going to go over. So that was the first one that we spoke about before, but what we could also do in this equation is again in the relationship sheet is use this one where V2 is equal to R2 over R1 plus R2 times Vs. Okay, so again I'm going to name these 2 resistors. I'll call the top one, the 7 ohm, call that R1, call the bottom one R2. So the voltage V1, that would be the voltage across this resistor. V2 would be the voltage across this resistor. So V2, that's the voltage across the 15 ohm resistor. That's what we're being asked. And of course that would be equal to 15 divided by, what did we say? R1 plus R2 is 7 plus 15. Now, be careful with your calculator. And just so there's no mistake, put this because the bottom line should really be the total resistance in the circuit. Put that in brackets. Okay, so 15 over 7 plus 15, or of course you could just put in 22, times the supply voltage of 5 is equal to, now have a think about it, what kind of value do we expect? So I guess the value we expect, if these were both 7, you would expect 2.5 volts, 2.5 volts. This is roughly twice as large as this. So you would imagine this would get 2/3 of 5 volts. The voltage across the 7 ohm would be 1/3 of 5 volts. So again, you should have it's going to be more than 2.5. You should have a rough idea of what the voltage should be, just so that if you do press the wrong button, then you'll know about it. You'll not just move on to the next question, you'll do something about it. Right, the voltage I'm getting is, now this is one of the cases where I can show you the calculator. We've got 3.4090909009. You don't want to write down all these figures, or this is one of the questions where you are going to lose marks. So again, we go back to the rule, which is that, of course, here we've got 2 significant figures, here 2 and here 2. So I guess we want to write our answer to 2 significant figures. Again, if I was to write 3.41, wouldn't be a problem. But there's the rule, that it should be the same number of figures as the data which has the least number. So as far as I know, that's that one question. Remember, there was that slide that I showed you before, which shows another way that this question could be asked. I'm flicking through lots of different diagrams, and twice so far I've found the wrong one. There we go. Right. So this is exactly the same question, but let's imagine that instead of this circuit on the left being drawn, you're given this circuit, the one on the right. And you'll see the question's actually worded in a different way. It's saying a pupil sets up an electric circuit as shown in the diagram. Calculate the output voltage. This catches a lot of people out. So it's not saying calculate the voltage across the 7 ohm. It's not saying calculate the voltage across the 15 ohm. It's just saying output voltage. So it's important to know that the output voltage, I'll point to it here, that point here, the output voltage at this point, that is equal to the difference between the voltage down here, 0 volts. It's always measured from 0 volts. So we've got 0 volts down here. We've got output voltage here. What's in between 0 volts and the output is, of course, this 15 ohm resistor. Okay, now if the circuit as well is drawn like this, if the potential divider is drawn like this, now this could be part of a transistor switching circuit, and it's always really important to work out that you're working out the voltage across the bottom resistor in transistor switching circuits at least. If I'm asked for the output voltage here, it is measured from 0 volts down here to this point. So as I said, that's the voltage across the 15 ohm resistor. In fact, I'm not working out anything out, or not, I'm not working out anything new in this question because we have the answer. This was it. So we know this one equation could be used, but if this is the equation you've been using most of the time, just remember there could be questions where you're asked to also work out the current. So if you're asked to work out the current, this won't be a method which can be used. Great for working out the voltage, but just make sure you also know that you would add the 2 resistances together to get the RT. Once you've got that total resistance, work out the current, and then you can use V equals IR to work out the voltage across the 15 ohm. Now, I think we've only got one more question before we start on the transistor switching circuits themselves, and I am keen to get onto those. It should be this question. I think it's a quick one as far as I remember. There we go. This sort of links into transistor switching circuits anyway. Now remember we said if there are 2 resistances in a potential divider, also known as a voltage divider, then the resistance, or the resistor, which has the largest resistance, it will have the largest voltage across it. The other important thing is, no matter what these two voltages are, we've got V1 and V2, they always have to add up to the supply voltage. Okay? Now if we look at the question, it says a circuit is set up as shown. The initial reading on voltmeters V1 and V2 is 6 volts. So we know, actually there is another equation I've not mentioned yet, which can be useful, which is that the ratio of the voltages V1 over V2 is equal to the ratio of the resistances. I'm not actually going to use this equation right now, but the fact that V1 is equal to V2 tells me that R1 is equal to R2. So it must be that whatever the value of that resistor on the right is equal to the resistance of the thermistor is the same. Now the question says, what will be the effect on voltages V1 and V2 when the thermistor is heated? Now this is the point you need to remember. Your LURD, LURD and TURD. This one is obviously for a light dependent resistor and stands for light up, resistance down. For this one, what we've got obviously is a thermistor. We saw that before in the circuit symbols. When temperature goes up, the resistance goes down. So in this case, what's going to happen, we're going to heat that thermistor. I guess, let's see, I could write this out now. When you're explaining transistor switching circuits, you might see, your teacher might write out the explanation of how the circuit works in shorthand. You obviously would want to write that out as clearly as possible, and as I said, I want to get onto a question like that. So when the temperature increases, then the resistance, I'm going to call it RTH, the resistance of the thermistor is going to decrease, and therefore the voltage across the thermistor, VTH, as we said, the larger the resistance in a potential divider, the larger the voltage across it. So if that resistance is decreasing, the voltage across the thermistor is decreasing. Okay? Now it's not in the circuit, it's not labelled as V1, sorry, it's not labelled as VTH, it's labelled as V1. So in other words, V1, when the temperature goes up, the resistance of the thermistor decreases, the voltage across the thermistor is going to decrease. So yeah, in this question you'll be talking about the voltage V1 would be decreasing. Obviously that would then cause V2 to increase, but you would write this out as a sentence. You wouldn't use this shorthand, so don't write like that. One thing to note as well, that what caused this voltage to decrease was the fact that the resistance of the thermistor decreased. And where some people go wrong is they think that this voltage V2 increased because, if I can again use my special pointer, there we are, they think it's because that resistance has increased. It's not. It's just the fact that in the divider, the voltage across each, well, when you add the two voltages, in this case, always has to add up to the supply voltage. So the fact that this voltage has gone down has caused this one up, even though the value of that resistance is constant. It's not changed. Now let's see, I said I wanted to get on to transistor switching circuits. Let's see if I can find it. So it's this one, hopefully. Here. Now, what does it say? A physics teacher builds an electronic circuit to demonstrate how street lights can be switched on automatically in the dark. Name components X and Y. Now, in fact, two of the circuit symbols that I didn't show at the start, the circuit symbols for an NPN transistor and a MOSFET. They are both transistors, but you need to be able to differentiate between the two. So use those labels, NPN transistor and a MOSFET, which stands for metal oxide semiconductor field effect transistor. You don't need to remember that at this level. So yeah, what we looked at a circuit with a thermistor before. This is an LDR, light dependent resistor. So LDR is circuit symbol X, symbol Y is the MOSFET. Now this circuit, once we speak about how it's going to work, operates in exactly the same way if, or even though, this MOSFET were replaced with the transistor, the NPN transistor I should say. The only thing is, it would switch at a different light level. I'm not going to go into that at this point. So we've named the two components. We'll go on to the point I really wanted to get onto was this, where we had to explain how the circuit works. Now this is one of the other lessons I guess that I want to put online, because this is the kind of thing a lot of pupils struggle with, transistor switching circuits. So let's see. Now we said before in the potential divider that if you wanted the output voltage, which I guess would be here, this is the output voltage, then it's the voltage across this bottom component. Now in these circuits, the most important voltage is the voltage across this bottom component, and you're looking for what I guess could be called the active component in this circuit, something where maybe heating it up, shining more light or less light on it is going to change its resistance. So in this circuit, it's this LDR. You want to talk about its resistance and therefore the voltage across it. And if that component, the LDR or thermistor, I guess is down here, that'll be easier to explain than if it's up in this position. I'll show you that kind of circuit later. So how does the circuit work? Well, the voltage across this bottom resistor, which in this case an LDR, is also the voltage, I guess, which is responsible for switching on this MOSFET. The voltage between this point and this point here. Okay, so we're interested in the voltage across this LDR. So again, I'm going to write this in shorthand. Don't write this in shorthand yourself. You would be talking about, I guess what you want to do is you want to make the voltage increase above a certain value to then allow this MOSFET to conduct. So in order to get that voltage across the LDR to increase, you want its resistance to increase. So its resistance is going to increase in the dark. So when the light level goes down, you would then be talking about the resistance of the LDR increasing, and therefore the voltage, again you would be writing this out in full, the voltage across the LDR would then increase, and then when that voltage is above a certain value, this MOSFET would then conduct. When this conducts, now see this one branch in this circuit, that's the potential divider, a voltage divider. Other branch is the MOSFET in series with, could be a motor, could be a buzzer, could be, in this case, a relay. So yeah, once the voltage across this increases above a certain value, the MOSFET conducts, and we'll have a current in this branch. So basically there'll be a current in this coil that would then close this switch, and the heater would come on. Now I should have, if I click here, a typical answer that you'd be writing. So as it says, in darkness, the resistance of the LDR increases, so the voltage across the LDR increases. Now, important thing is, I'm not just saying resistance increases. I'm not just saying voltage increases. Really important, this part here, that you're mentioning the resistance of the LDR. Now, in case you don't know, it's a resistance of something, current in something, or voltage across. So resistance of, power of, voltage across, and current in. Okay? So as we said, the resistance of the LDR increases, so the voltage, you don't just say again voltage increases, you have to talk about the voltage across the LDR increases. Then I'm saying it again, the voltage across the LDR, when it increases above a certain value. Now if you know that value because you've been told it in part of the question, then you would state it. We're not told that value, so it's enough to just say when this voltage across the LDR increases above a certain value, the MOSFET conducts. And as we said, when it conducts, we have a current. So when it's conducting like so, we'll have a current here in the relay coil. Now the relay coil, as we said before, acts like an electromagnet. That then causes this switch to close. And what we've actually done is use a low voltage. This could be a 5-volt circuit. Used a low voltage here to then switch on a 230 volt circuit. So this, remember we said before about the relay. The relay is normally drawn with a dotted line. So we've got two parts to it, the coil, which acts as an electromagnet, and the switch. So a current in this coil then closes this switch, and of course we've got a current in this circuit. This heater would then come on. Now just quickly, I'm aware of the time and I just want to show quickly the second part. The second part, in case you're wondering what would happen if I was to switch the two components. So that's what I've done. You can see I'll get rid of this part, I'll get rid of the pointer. I've also blanked out the question because this isn't a circuit. It says a physics teacher builds an electronic circuit to demonstrate how street lights can be switched on automatically in the dark. This circuit wouldn't switch on in the dark. It would now switch on when it becomes light. So that's important to know. If you switch the two components, the circuit's going to do the exact opposite. So if you've got, say, a thermistor down at the bottom, if you have a thermistor down here, then hopefully you would know that that would be a circuit which would switch on in the cold. If you want a circuit which switches on when it becomes hot, move it, the thermistor up here. So before we had an LDR down here, that allowed the MOSFET then to conduct when it became dark. Switch the two, this is now a circuit which switches on when it becomes light. Now I'm still really interested in this voltage down here, but we have to talk about how the light level switches on the MOSFET, not varying the value of this variable resistor. So despite the fact I guess I want to get on to talk about this resistance, in fact not the resistance, this resistance won't change. I want to get on to talk about the voltage across this variable resistor, but I have to start with the LDR. So how do we get the voltage across this resistor to increase, which is then, as we said, it's going to switch on the MOSFET or allow the MOSFET to conduct. Basically, we have to talk about this voltage first. So if this voltage across the variable resistor is increasing, that's because the voltage across the LDR is decreasing. Now I'm going to get rid of what I've written down, and where you would start, you would say that when it becomes light, the resistance of the LDR decreases, therefore the voltage across the LDR decreases. Now we can talk about this part of the circuit, the part we're really interested in. So if the voltage across the LDR decreases, the voltage across the variable resistor increases. And then we can talk about if it increases above a certain value, then this MOSFET is going to conduct. And then we can talk about this current. So we'll have a current in the relay coil, which acts, as we said, like an electromagnet. So when we have a current in the relay coil, that then closes the relay switch, and we've got that heater to come on. So as we said, switching these two components, I guess it goes from having a circuit which switches on, as we said, in the dark, to then having one that switches on in the light. Now, as I said, I'm aware of the time. I think I've covered enough there. Now, hopefully the quality of this video has been okay, so that when it goes onto YouTube, eventually the diagrams will be clear to see. What I will do when I've got time is to put the diagrams themselves onto my internet site. So if I was to go there, that will show you the URL, www.physics-podcast.co.uk. So as I said, that video should go onto YouTube, and then the actual diagrams that I've used will be put on the website, so you can download a PDF that shows you them. And again, you can maybe try the questions with a piece of paper, and after that point then take a second look at that video. But that's us for now. So thanks very much for watching. Next lesson will be same time next week. So next Tuesday, 6:15, and we'll see you later. Bye.